Good morning, everybody. My name is Timothy Park. I'm a third-year civil engineering student at SDSU, and under the supervision of Professor Ferroni, I'd like to present to you my research on the mechanical properties of seawater glass fiber reinforced concrete. Just going over quickly, a quick overview. I'm just going to quickly introduce my project and the hypothesis, give a quick overview, and give results, conclusions, and future directions. So to introduce, I'm just going to address a problem within coastal projects. Within many coastal projects in, for example, Louisiana as well as California, we deal with using seawater within our concrete as an economic alternative to freshwater. This is because freshwater is a lot more expensive to transport and use within these coastal projects. With that in mind, the problem with using seawater is that when we do incorporate it within our concrete columns and concrete projects, there's a degradation in not only the concrete itself, but especially within the steel reinforcement, which compromises the structural capacity of our buildings. With this in mind, we want to look at using glass fiber reinforced polymer as a substitute to steel reinforced concrete. This material essentially, what it does is it's an anti-corrosive material. So as a result, if we use seawater concrete within these concrete columns, we can see that maybe there's a possible chance at possibly reversing the damage done by seawater within our concrete. With that in mind, we hypothesized with our experiment that the GFRP will exhibit greater structural capacity under load, as well as lasting longer than traditional steel reinforced concrete. The implications of this, like I said, were in coastal projects. We can see this being used in the future within coastal projects within California, and possibly for better prepared use within seismic loading. Quick overview of our project. We're going to start off with small-scale comparative testing between the freshwater and seawater concrete using the GFRP rebar as well as the steel reinforced rebar. Then we're going to transfer that with the data given to a larger scale model with GFRP, and then further on into a seawater integration and testing of that column. So to start, I wanted to talk about our small-scale comparative testing. This is phase one of our project and the current phase that we're on right now. This is to assess the concrete's performance using seawater as well as freshwater without any support, with steel support and glass fiber support. We are going to use 24 by 48 inch cylinders testing over 3, 7, 28, and 90 days. To test this, we are going to put it under a compressive strength test, and then what's known as a Brazilian split test in order to test the tensile range of the cylinders. Also, to test the water and the concrete as well, we are going to test for the pH and organic material as well as the sulfate content within these concrete samples to sort of see what the water does to the concrete and how it affects the overall strength capacity of the concrete. Once we get our data, we want to convert that into phase 2 and phase 3 of our project, which is a much larger scale model. This is to examine the concrete's behavior in real-world situations and real-world simulations. To do this, we're going to use a much larger column with a lot more reinforcement within our concrete samples. We're going to then put it under, likewise, a compressive load as well as a shear transverse load in order to simulate seismic loading on our concrete for real-world environments, specifically in California, which is very prone to earthquakes. So the results, we've only been able to go as far as phase 1. Thanks to the previous work of Professor Ferroni's students, we were able to get preliminary data on this project. As you can see here, the dotted line represents the concrete without any support, seawater and freshwater, and then the solid lines at the top represent concrete with the support, with steel reinforcement support. As you can see from that data, we can see that the seawater definitely degrades the concrete a little bit, especially when steel reinforcement is added. If you look to the bottom, you can see that there is an outlier. This is actually the concrete used with glass fiber reinforcement. Now, this outlier may seem concerning for our research. However, there is an explanation for that. For this experiment specifically, instead of using glass fiber reinforcement as a mechanical reinforcement, we use it as an actual chemical add-in, essentially like a fine particle dust that we put into our samples. This affected the overall chemical composition, and the material itself turned out very spongy and not very good. So it's something that we are going to address in further research and further experimentation, which I will explain in the next slide. With this in mind, the conclusions of our experiment, we can deduct that the seawater incorporation within concrete is definitely not as good, or it's definitely deleterious on the strength of the concrete, and that adding the GFRP as a chemical add-in can significantly decrease the overall strength of the concrete. A couple of future directions. We want to address, first of all, a problem with the concrete and GFRP as an add-in. I have another project coming up that I'm very excited to start. We are working with a local surf company and working with their and using the waste product, a polyurethane byproduct of like creating the surfboards, as a potential add-in to our concrete. This is more of a foaming agent for our concrete, creating higher volumes of concrete. And this is to possibly address using an add-in for our concrete. With that in mind, we are going to continue development in phase 1 and phase 2 using the GFRP as a mechanical reinforcement rather than an add-in, and then carrying on from that into phases 2 and phases 3. With this in mind, I wanted to extend my gratitude to Jessica Rubio, Tegan Goodman, and Josiah Imperial for supplying the initial data on the compressive strength of concrete. I'd also like to thank Professor Robert Dowell of SUSU for his help during the drafting of phases 2 and phases 3. Thank you for your time, and I would like to open it up to questions now.